Okay, so in today's lecture, we'll start with surge impedance loading. Clear? Surge impedance loading means it is the power transferred by a lossless line to a resistive load. It is a power transferred by a lossless line to a resistive load whose impedance equal to surge impedance of the line. So in short, we write SIL, surge impedance loading means what is mentioned? It is the power transferred by a lossless line to a resistive load. It is the power transferred by a lossless line. Power transferred by a lossless line. Lossless line to a resistive load whose impedance equal to surge impedance of the line. Okay, so careful. Surge impedance load we are defining for lossless line or lossy line? Lossless line. Let's say this is what our lossless line. It's a lossless line. Fine. It's a lossless line. Then chalo. Now we are connecting a load at the receiving end such that whose impedance. Why I am showing resistance? Because surge impedance is what purely resistive. Correct or not? Clear? So, and one more important thing is that, okay, under this condition, whatever the power we are transferring to the load, that is called what? Surge impedance loading. But voltage across the load is VR. The current at the receiving end is what now? IR. Okay, now this is the, circuit for under surge impedance loading. Now tell me, whatever the power we are transferring to the load means what? The power at the receiving end, I can say. The power at the receiving end is what? PR. Power drawn by the load is what? PL. Both are same because we are not providing any compensation here. Okay. So the point is very clear now. Under this condition, whatever the power we are transferring is called what? Surge impedance loading. Yes or not? Now tell me, the current at the receiving end is what now? IR here. IR equal to what now? IL. Is it clear? Now tell me, what is IR and IL here? First of all, IR equal to IL. That is equal to what? VR by R. Otherwise, you can write VR by ZS. Correct or not? But tell me, we can also write from here VR equal to what? IR into ZS. This is also valid. Next important thing. Let's see. What is the power drawn by the load? Surge impedance loading means under this condition, whatever the power transferred by the line, that is receiving end power, that is equal to what? Load power. So what I get now? 3 into VR square by ZS. Why we got 3 into VR square by ZS? Better to say R. Since it is a three-phase system, the power drawn by this load resistance. Why I am saying load is resistance? Under surge impedance loading, ZS is what? Purely real number. Real number means resistive load only. So under surge impedance loading, load must be what? Resistive. Again I am defining, just check. Surge impedance loading means it is a power transferred by a lossless line to a resistive load. And whose impedance or resistance equal to what? Surge impedance of the line. And surge impedance also resistive. That's why matching is done. Now you can also say this is what? 3 into VR square by what? ZS. Because R equal to what now? ZS. Clear? Now tell me, VR is the phase voltage. What about the line voltage? Line voltage we can write what? VRL by root 3. VR equal to VRL by root 3. If you do that, we get what? Root 3 square and 3 get cancelled. Directly I am writing surge impedance loading is what now? VRL square by ZS. So finally, what is the formula for surge impedance loading? Surge impedance loading is what? PRL square by ZS. Suppose if the question is given like this, for a 400 kV transmission line, for a 400 kV transmission line, what is surge impedance loading? Does he mention anything about the surge impedance? No. But what is this 400 kV? VRL. VRL only. So line voltage only and VRL only. So directly you can write what is the surge impedance loading now? VRL square is what? 400 square by what is the surge impedance of the line? 400 ohms by default. If it is not given means you have to take 400 ohms. So but we get it in megawatts. Why? K square will give you mega. So what is the answer now? 400 megawatts. That means if the surge impedance is given means you have to take it. If inductance and capacitance given means you have to calculate. Suppose if the surge impedance is not given in the problem, then what? Surge impedance not given and inductance capacitance also not given, then what? You have to take, you have to consider 400 ohms. Clear? Understand? Okay. So that's it. So that's about surge impedance loading. Understand? So the formula for surge impedance loading. Now we will write some important conclusions. The first conclusion is, under surge impedance loading, tell me what about load? Load is purely resistive or inductive or capacitive or RL or RC na? It's a purely resistive load. Correct or not? And now tell me, what is the load current IR? What is the load voltage VR? IR and VR are in phase. Why? Because load is purely resistive. IR is the load current or receiving end voltage. Receiving end current. VR is the receiving end voltage. Both are in phase. Why both are in phase? Very simple. Because load is purely resistive. And what about the receiving end power factor? Unity. Load consumes active power but not any reactive power. Why reactive power do not consume? Because it is a purely resistive load. Correct or not? So these things I am going to write now. The first conclusion is that. So what I can write? Conclusion number 1. You write like this always. Under surge impedance loading. What is the first thing? About the load we are writing. Load is purely resistive. Load is purely resistive. Number 2. Load impedance is equal to surge impedance. Load impedance equal to what? Surge impedance of transmission line. So what I can write now? ZL equal to what? ZS. That's the meaning. Next. VR and IR are in phase. What is the meaning from this? Theta R equal to 0. What about receiving end power factor? Receiving end power factor is what? Unity. Because receiving end power factor means cos theta R, that is what? Cos 0, that is equal to what? 1 now. Correct or not? And the next point. Load consumes only active power because it's a resistive load. Load consumes only active power but no reactive power. These are the things very important. That means what is the QR value? 0. What is the PR and PL? PR and PL equal to what? VRL square by ZS. This is nothing but what? Surge impedance loading only. Okay? Clear, sir? Now this is the one thing which is very important under surge impedance loading. Now the second thing. To write the second conclusion, I will go back to the previous lecture where we discussed this lossless line. See, for lossless line, what are the parameters we discussed? Chalo. These are the equations we discussed for lossless line. For lossless line, you remember ABCD parameters of lossless line. There we concluded about this. I just want to copy this. Okay, let's go back. Now, I'm going to write the second conclusion. Under surge impedance loading. Now tell me. So this under surge impedance loading, just notice what happens. What about VR and IR-ZS relation? Because see, under surge impedance loading, IR-ZS is nothing but what? IR-ZS is nothing but what? VR only. Correct or not? IR into ZS is nothing but VR only. Under surge impedance loading, I am saying. So under surge impedance loading, so IR-ZS is what now? VR. Correct or not? Let's see. If you have any doubt, go back, check here. What we written? VR equal to what? IR into R. Otherwise, VR equal to IR into ZS. Okay. So if I substitute that, what I get now? So this is V of X we copied. Now I want VS and IS. Okay, chalo. Even for lossless line, just check. This I am deleting because we copied the other one. We will discuss this later. Okay, right? So first we'll discuss about VS and IS. Okay, let me go back once again. Yeah, for lossless line. Chalo. For lossless line, what is the relation here? Yeah, this one I want to copy. See, for lossless line, these are the relations. VS equal to VR cos beta L, J IR ZS sin beta L. IS equal to IR cos beta L, J into VR ZS by sin beta L. Even under surge impedance loading only, we are discussing about lossless line. It's not lossy line. Correct or not? So for lossless line only we are discussing. That's why what I will say here. Yeah, think about it. So we can replace IR ZS with what? VR. If I take VR common, what I get now? Cos beta L plus J sin beta L. Directly I am writing. I am replacing this term. Careful. This VR ZS as what? IR ZS is VR and VR by ZS is what now? IR. Now, if that is the case, I can take here IR common. Then I get what? Cos beta L plus J sin beta L. Now tell me, what is the magnitude of cos beta L and sin beta L? Magnitude of this is what? 1. Phase angle is what? Tan inverse imaginary part. Imaginary part is sin beta L. Real part is cos beta L. Tan inverse tan beta L will be the beta L. So that's why I can write directly. This is VR at an angle what? Beta L. And this is IR at an angle beta L. Now what you can understand from here? So under surge impedance loading, finally, what is VS? VR beta L. What is IS? IR beta L. From this, what I can conclude? Already we discussed one thing. Under surge impedance loading, VR and IR are what? In phase. Correct or not? If you draw the phasor diagram, this is VR and IR in phase. In the previous case we discussed, because the load is purely resistive. VR and IR are in phase. But tell me, what about VS? VR at an angle beta L. Magnitude is VR, but phase angle is what? Beta L. Positive or negative? Positive. Positive angles are what? Shifted anti-clockwise direction. So, this is the position of what? VS. But length of the VS, length of the VR same. Why? If I see magnitude of VS, that is what? VR only. Magnitude of VS, VR only. So that's why length of the VS vector and length of the VR vector are what? Same. You need to take care of that. What is this angle called now? Load angle. The angle between VS and VR are called load angle. We know this. But what is that load angle? Beta L. And one more thing. What is the IS? IR at an angle beta L. That means what? VS phase angle beta L. IS phase angle also beta L. So that means what? VS and IS are what? Again in phase. Again, length of the IS phase or length of the IR phase are same. Why? Magnitude of IS equal to magnitude of IR. See, this is the phasor diagram which is very, very important. Now from this phasor diagram, what I can write? Under surge impedance loading, what is the load angle? under surge impedance loading. What is the load angle? Load angle, that is what, delta, that is equal to what, beta L. The load angle is beta L when under surge impedance loading. Okay, clear? Now the next important thing is, okay, what about magnitude of Vs? Equal to what, VRL. That means what, the sending end voltage and receiving end voltage are in same magnitude. What about magnitude of Is? That is equal to what, IR. Now tell me, shall I say Vs, Is are in phase now under surge impedance loading? Vs, Is are in phase, correct or not? Vs angle and Is angle same, that's why nothing wrong to write Vs and Is are in phase. Vs and Is are in phase, Vs, Is are in phase means what? Theta S is what now? 0. If that is the case, what about sending end power factor? That also unity. Sending end power factor. Unity. So that means power factor of the sending end equal to is what, unity. Okay, now tell me, under surge impedance loading, what is the complex power at the sending end? Complex power at sending end. Complex power at sending end means what? SS. How to write that? How to calculate that? Simple. What is the formula we use? SS, that is equal to what? 3 into Vs into what? Is conjugate. In the real part is active power, imaginary part is what? Reactive power. Let's substitute now. 3 into Vs means what? VR at an angle beta L. Now Is conjugate means what? IR at an angle beta L. Is equal to IR at an angle what? Beta L. So now I'll get minus beta L. So what I get now? 3 into VR IR. But we know IR is what? VR by ZS. Now continuation. So we can write now 3 into VR square by what? ZS. Simply VRL square by what? ZS. This is the real part. What about the imaginary part? 0. That means what is PS? VRL square by what? ZS. And what is QS? 0. That means under surge impedance loading, line draws only active power from the sending end, but no reactive power. That's what I can write. Okay, clear? If you have any doubt, you can check this derivation. I hope you understand this. Okay, just go through it. Yep. So what I can write from this discussion under surge impedance loading. Yep. Under surge impedance loading. Next conclusion. Sixth conclusion. Under surge impedance loading. The source. The transmission line draws only active power from the source. But no reactive power. So we already got that PS equal to what? VRL square by ZS. And QS is what now? 0. But have you noticed one thing? What is PR value we got? VRL square by ZS only. What is QR? 0. What is the meaning? There is no reactive power loss in the line. Yes or not? QS 0 and QR 0. QS minus QR is called reactive power loss. And what about the active power loss? Yes, it is also 0. Why? PS is VRL square by ZS. PR also VRL square by ZS. So active power loss also 0. So that means what I can write under surge impedance loading, PL equal to 0 and QL equal to what? 0. And what about the efficiency of transmission? 100%. Efficiency of transmission is 100%. That is true. Why? Because we are dealing with lossless line. Okay? Correct or not? It's not lossy line, right? Think about what is the definition of surge impedance loading. It is the power transferred by a lossless line to a resistive load whose impedance equal to surge impedance of the line. Means what? We are dealing under surge impedance loading a lossless line but not a lossy line. So that is the reason why I am saying, okay, see, efficiency of transmission is 100% and losses also 0. We just proved now. Correct or not? Okay, if our analysis is correct, means what? Loss should be 0. Yes, we are getting the loss is what? 0. Right or not? So that is what under surge impedance loading. Okay, clear, sir? Now, third conclusion also we can write now. We will go for now third conclusion. Let me write here. Conclusion number 3. Under surge impedance loading. Now, again, we can go back for lossless line. Lossless line. What we derived lossless line? Yes. These equations we are going to take. This is what? Lossless line, the characteristic equations. V of x equal to, is this now? Correct or not? I just want to copy this. Okay, chalo. So now tell me from this what I can write? Just similar to the previous. IRZS is what now? IRZS is what? IRZS is what? VR. VR by ZS is what? IR. If we substitute that, what I get now? VR at an angle beta x. Directly I am writing. What is this? IR at an angle beta x. I hope you understand how I written directly. See, VR cos beta x plus VR sin beta x. J VR sin beta x. Magnitude is VR. Phase angle is what? Tan inverse of imaginary part by real part. We get beta x. Correct or not? Here also. IR cos beta x plus J IR sin beta x. IR, if you take it common, magnitude is 1. Phase angle is beta x. Right or not? So finally, what we got under surge impedance loading? V of x equal to VR at an angle beta x. I of x equal to IR at an angle beta x. This is what under surge impedance loading. Correct or not? Clear? Now tell me. So, from this what I can understand? The magnitude of V of x equal to VR. Magnitude of I of x equal to IR. But what is this V of x indicates? X means what? It is a distance measured from the receiving end. See, x equal to 0, x equal to 1, x equal to 2 meter, 3 meter, any value of x you substitute. But magnitude is what? VR only. Because this side it is not function of x. VR, just VR, that's it. So that means at every point along the line, magnitude of the voltage is same. That's what we can understand. Similarly, at every point along the line, the magnitude of the current also what? Same. That is equal to what? IR. Correct or not? So let me write these 2 points now. So the first point is the surge impedance loading. What we understand? The magnitude of V of x equal to what? VR. From this what I can conclude? At all points along the line, the magnitude of the voltage is constant. The magnitude of voltage is same. At all points along the line, the magnitude of voltage is same. Correct or not? Clear? Understand? Now, what else we can write? At all points along the line, the magnitude of the current also same. Na? But before that, I can draw some characteristics here. If I plot x versus magnitude of V of x. x0 means you are at the receiving end. Correct or not? x0 means you are at receiving end. If you are traveling from receiving end to sending end, everywhere, maybe this is x equal to L. This is nothing but what? Sending end. But all the points, the voltage magnitude is what now? Same. Correct or not? Now similarly, we can copy this for current also. You can replace V with what? I. Yes or not? Now tell me, at all points along the line, what about the magnitude of the current? Magnitude of the current, same or not same? Yes, it is same. Correct or not? Okay, at all points along the line, the magnitude of current is same. The magnitude of current is same. At all the points along the line, magnitude of current also same. That's what conclusion number 2. Okay. In case of third conclusion, this is the second part. Okay. Clear? Understand? Next, one more important point. At all points along the line, voltage angle is what? Beta x. Current angle also beta x. What I can write now from here? If this is V of x and I of x also here. So that means at all points along the line, voltage and currents are what? In phase. That is the third thing. At all points along the line, voltage and currents are in phase. Voltage and currents are in phase. Voltage and current are in phase. So that means, what is the meaning? There exists unity power factor. Correct or not? There exists unity power factor, because voltage and current in phase means angle 0 means power factor is what? Unity. So that's why there exists unity power factor at all the points along the line. There exists unity power factor. This is also very, very important. Power factor at all points along the line. At all points along the line. At all points along the line, there exists what? Unity power factor. Unity power factor. Right or not? Clear? Understand? Any doubts here? Okay. Chalo. Next one. You can calculate now the complex power at any point along the line. Complex power as a function of length. Okay. Complex power S of x. What is this S of x? Just like SS. We can write 3 into V of x into I of x conjugate. In this, real part is what? Active power any point along the line. And imaginary part is what? Reactive power any point along the line. Now let's calculate what I get. S of x. 3 into V of x means we are at an angle beta x. I of x means what? I are at an angle what? Minus beta x. Now what I get now? Again 3 into VR IR. So what I get now? 3 into VR into IR is what now? VR by ZS. Now I can write 3 into VR square by ZS. 3 VR square can be written as what? VRL square. VRL square by ZS. That is what the active power. And reactive power is what now? 0. That means at every point along the line, the active power is what? VRL square by ZS. But the reactive power, Q of x, is what? 0. First we'll talk about this, active power. Why active power is same at any point along the line? Because we are talking about the lossless line. There are no losses. For every section, if you see, the losses are 0. You can divide the transmission line into thousands of sections. Do we have any loss in any section? No. Why? We have neglected the resistance and conductance. That's why section 1 active power is 100 megawatt. Means section 2 also same power is going without any loss. But why this reactive power is 0? How to understand this? From this we can understand reactive power consumption and generation both are same. Because we are assuming it's a lossless line, but inductance is there and capacitance is there. Every section there exists an inductance and capacitance, like this from sending end to what? Receiving end. You understand? Every section there exists an inductance and capacitance. What is the meaning of this is, inductor consumes the reactive power, capacitor supplies the reactive power. But Q of x 0 means what? Whatever the reactive power consumed by the inductor, whatever the reactive power supplied by the capacitor, both are same. That is the reason Q of x becomes 0. Means what? The line generates the reactive power, line consumes the reactive power, fine, but both are matching. In what form line consumes the reactive power? Because of inductive nature. In what form line supplies the capacity power, supplies the reactive power? Because of capacitance. That's why the point is what? The reactive power consumption and generation what? Same here. Even we can prove this also mathematically. Yes, let's see how to prove this. So, but before that, what I can write? At all points along the line, the active power remains same. Correct or not? At all points along the line, active power is same. Active power is same. But reactive power is 0. Reactive power is 0. What is the meaning of this? P of x is, again, let's copy paste this. VRL square by ZS. And Q of x is what? 0. Now, clear? And I'm going for next point. Since Q of x 0, what it indicates? Q of x 0, na? What it indicates? Q of x equal to 0, what it indicates? It indicates reactive power consumption of x equal to what? Reactive power generation of x. Yes or not? But tell me, what is the reactive power consumption formula? Reactive power consumption of x equal to what now? 3 into magnitude of IR square. Because, okay, let me write I of x whole square, better. Magnitude of I of x. Because at any point along the line, what is this? I of x. But any point along the line, the reactance is what? Small xl. 3 into I of x whole square into what? Small xl. We can also write like this. Magnitude of Ix is nothing but IR. 3 into IR square into what this? Omega L. This is what? Reactive power consumption. Now tell me, what about reactive power generation of X? 3 into magnitude of VR. Magnitude of V of X. By what? Xc. Xc is the capacitive reactance. Now tell me, if I substitute, what I get? 3 into VR square. Why? Magnitude of V of x is nothing but what? VR. At every point along the line, the reactance is what now? Sorry, at every point along the line, V of x is nothing but what? VR. Magnitude of V of x is nothing but VR. So, VR square. 1 by xc is omega c. Xc equal to 1 by omega c. So, directly I am writing omega small c. Now tell me, from this, what I can write is, check here, VR equal to what? We know IR into ZS. I can replace that. 3 into IR into ZS square into omega c. So 3 into IR square. What is ZS? Root over L by C. Na? So ZS square means what? L by C into omega c. CC get cancelled. What I get now? 3 into IR square into what? Omega L. Nothing but what is this? This only means Q consumption of X. Finally, Q generation of X equal to what? Q consumption of X. What you can understand? What you can understand? Under surge impedance loading, at every point along the line, under SIL, under surge impedance loading, at every point along the line, so on the same conclusion only we can write this. At every point along the line, reactive power consumption and reactive power generation in the line are same. Generation of line reactive power consumption of line and reactive power generation of line are what? Same. That's why what happens now? Transmission line act as what? What the transmission line act as under surge impedance loading? Just think about. Neither source nor sink for what? Reactive power. Yes or not? So under surge impedance loading, the transmission line act as neither source nor sink for reactive power. So hence under surge impedance loading, transmission line act as neither source nor sink for reactive power. Clear, sir? This is a very important thing. Now, the next important thing is that under surge impedance loading, what is the reflected voltage and reflected current along the line? That also we can conclude. What is reflected voltage and reflected current? So that I will go back to that expression. Okay, please. I'm going back to where we defined reflected voltage and reflected current. Let's see. It's long back we defined. Chalo, here. See, under surge impedance loading, we need to see what is these values. Okay, this is what reflected voltage wave, right or not? What I get here, VR minus IR ZC by 2 now. Under surge impedance loading, ZC means ZS because lossless line. This is ZS. IR ZS is nothing but VR. VR minus VR is what? 0. That means there is no reflection. Under surge impedance loading, that means if you have a transmission line, okay, if the voltage wave is traveling along the line, it reaches the receiving end. There also, the load having the same impedance as what ZS, then there is no reflection. Reflected wave is 0. Okay, similarly, let's see. Reflected current wave also what? VR minus IR ZC. IR ZC is nothing but IR ZS. Lossless line means ZC is ZS. Right or not? So IR ZS is what now? VR. So VR minus VR again what? 0. So that means there is no current reflection and what? Voltage reflection under surge impedance loading. Okay, let me write that. So conclusion number 4. Under surge impedance loading, under SIL, reflected voltage wave equal to 0. Reflected current wave also equal to 0. Okay. In fact, no reflection along the line. Transmission line not experience any reflection. Okay, what is the meaning here? Indirectly, this is a line having a surge impedance ZS. Now, it is terminated with what? Load impedance ZL equal to ZS. The voltage coming here is what now? Incident voltage V. But the reflected voltage here is what now? 0. That means whatever the voltage will come here now, that will go as it is. If this is V, this is also V. You understand? This is called V means what? Hello. It is a traveling voltage. Okay. Otherwise, incident voltage is coming here. Reflected voltage. This is called refracted voltage. Also called transmitted voltage. Transmitted voltage and incident voltage both are what? Same under surge impedance loading. That's why under surge impedance loading, since there is no reflection along the line, so transmission line is called flat line or infinite line. You remember we started defining lossless line, lossy line, attenuated line, attenuation free line, distortionless line, distorted line, infinite line and flat line. First 6 definitions already I given in starting off analysis of long transmission line. Now I am going to give the remaining 2 definitions. And one more definition also we need to discuss, that is called tuned line. We will discuss that at the end. But at this stage I am going to define what is flat line and infinite line. Since there is no reflection along the line, so that's why line is called flat line or what? Infinite line. So under surge impedance loading, there is no reflection along the line. So under surge impedance loading, there is no reflection along the line. So transmission line is called flat line or infinite line. Flat line or infinite line. Flat line or what? Infinite line. When under surge impedance loading only. Infinite line. It is called flat line or what? Infinite line when under surge impedance loading. But is the surge impedance loading is ideal phenomena or practical phenomena? It is an ideal phenomena because practically you don't have a resistive load. Practically your line is what? Lossy line but not a lossless line. So that's fine. Surge impedance loading is an ideal phenomena. Okay, that is what fifth conclusion. Let me write here. Surge impedance loading SIL is an ideal phenomena. An ideal phenomena. Okay. So power transferred by the line under surge impedance loading is also called. So power transferred by the line under surge impedance loading is also called ideal power transfer capacity of the line. Careful, this is very, very important. Ideal power transfer capacity of the line. This is very, very important conclusion, Rabai. So what I am saying, ideal power transfer capacity mean ideal power transfer capacity or characteristic impedance loading. Surge impedance, characteristic impedance are both same for lossless line. Correct or not? Characteristic impedance loading or natural loading of the line. Sometimes it is also called natural loading of the line. Natural loading or simply surge impedance loading. All are same. What is this formula? Simply VRL square by what? ZS. VRL square by ZS. Clear, sir? Understand? Now we'll see the cable and overhead transmission line. What is the main difference between them? In case of underground cable and overhead lines, what are the major differences? Okay. One side you write underground cable, other side you write overhead transmission line. Okay. In case of overhead transmission line, you just think about. Overhead transmission line, spacing between the conductors are what? Very, 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 very high. But in underground cables, all the three cables are placed at the same location. We dig the ground at one point. There we lie all the three cables, R phase cable, Y phase cable and what? B phase cable. Spacing between them is very low. So spacing between them is low means what? GMD is low. So comparison wise, what I can write here? GMD is high. What about here? GMD is low. What is the inductance definition? Inductance is directly proportional to ln of GMD by GMR. If GMD is high, inductance is high. And capacitance is inversely proportional to what? Ln of GMD by GMR. If GMD is high, ln function is high, capacitance is low. So that's why what I can write in case of transmission line, I can write L is high, but C is what? Low. C is low. But here L is low, inductance is low, but C is high. Cable having very high capacitance. Now tell me, what is the surge impedance? Root over L by C. Okay, which is high. What about surge impedance here? Root over L by C, which is what? Low. Because L low, C high, both factors will contribute for very low surge impedance. So that's why typical value here is what? 400 ohms, but typical value here is what? 40 ohms. Now tell me, what about surge impedance loading? SIL. Surge impedance is high. Surge impedance loading is V square by ZS. Surge impedance loading is low here. But here what? Surge impedance loading is high. But tell me, what about practical loading? Practical loading always greater than surge impedance loading here. Practical loading or economical loading. I will prove you this, don't worry. Economical loading always greater than surge impedance loading. But here in underground cable, practical or economical loading always less than surge impedance loading. The reason is very simple. For example, if I will take an example here. See, 400 kV line and 400 kV cable, 400 kV transmission line. Okay, 400 kV cable. Let's take it. What is the surge impedance loading here? 400 square by what? 400 megawatt. I will get what here? 400 megawatt. Yes or not? But what about surge impedance loading here? 400 square by what? 40. We get 4000 megawatt. Okay, fine. But tell me, I given you 400 kV cable, I given you 400 kV transmission line. Where I can transfer more power? You understand what I am talking? I given you two things. 400 kV transmission line I given, 400 kV underground cable also I given. Where you can transfer more power? Through cable, through transmission line. 100% through transmission line only. Why? Because in transmission line, conductors are exposed to air. Whatever the heat energy produced in the conductor, that can easily dissipated into the air, that can easily radiated into the air. But in case of underground cables, is the heat energy produced in the conductor can easily going into the ground or atmosphere? No. Why? After the conductor we have insulation, sheath, bedding, armoring, serving. There are so many layers. The heat has to pass through all these layers. That means heat energy dissipation is not proper in case of what? Underground cable. That's why definitely I will transfer very less power through underground cable and more power through what? Overhead lines. That is the one thing. But why I am saying practical loading is greater than this 400 megawatt. You remember power handling capacity of 400 kV line. 400 kV line. What is the power handling capacity? Power handling capacity is what? 800 MVA. 800 MVA. Assuming power factor is 0.8 power factor. 800 into 0.8 will give you what? 640 megawatt. This is the practical loadability of what? 400 kV line. You remember this is we discussed in starting class. In chapter 1, I told you when we come across this criteria for selection of operating voltage, there I clearly mentioned a 400 kV line is generally designed to carry 800 MVA power. Okay, typical power factor you take it 0.8, 800 into 0.8, 640 megawatt, but still greater than 400. But tell me, what about for underground cable less than 640 megawatt, right or not? Because a cable will carry less power than what? Line. So, practical loadability is 640 here, less than 640. But here what? Surge impedance loading 4000. What about 640? Even you take 640 also less than 4000 megawatt. That's what I am trying to say. The practical and economical loading of underground cable is less than what? The loadability is what here? Less than surge impedance loading. But what about here? Loadability is what? Greater than surge impedance loading. See, 640 is greater than what? 400 megawatt. The practical loading of overhead transmission line is greater than what? Surge impedance loading. But whereas underground cable is what? Less than surge impedance loading. You need to accept this. Okay? Clear? Understand? And we'll take one more table. One side we write loading equal to surge impedance loading. Other side we write loading is what? Greater than surge impedance loading. And one more side we write what? Loading is less than surge impedance loading. And what are the comparisons? Okay. These things we are going to write now. Okay. Clear? Understand? Chalo. Okay, so let's write like this. So I am writing here loading is equal to surge impedance loading. Okay, now let's see what happens. First important thing is, let's see what is loading. Loading is nothing but what? VL square by ZL. That is equal to what? VL square, line voltage square by what? ZS. This implies ZL equal to ZS here. This already we proved. First thing. What about the first thing here? Load power is VL square by ZL is greater than what? Surge impedance loading power VL square by ZS. From here what? Load impedance is less than surge impedance. Correct or not? Now similarly reverse here. Loading is what? Less than surge impedance loading. So from here ZL we get what? ZL we get greater than ZS. We get ZL greater than ZS. Okay, clear? Understand? That is the first thing. Right, and the next thing, let's have a look. What about load angle under surge impedance loading? Load angle equal to what? Delta, that is what? Beta L. Now tell me, what about the load angle here? Tell me, you are transferring more power here. If power is more, load angle also more. Load angle indicates how much power you are transferring. I told you clearly, if power increases, load angle also increases. So here load angle is what now? Greater than beta L. Compare it to this case having more power transfer, because loading is what now? Greater than surge impedance loading. For example, surge impedance loading for 400 megawatt. How much power you are transferring here? 400 only. But here what now? Indirectly you are transferring more than 400 megawatts of power. So that's why more load angle here. Similarly, what about the load angle here? Less. Means what? What is the load angle? Here the formula less than beta L, where beta is what? Phase constant. Remember from last slide, what is beta? Omega into root over L by C. Sorry, LC. I'm sorry. Omega into root over LC. Omega into root over LC is what? Beta. Okay. Next. Tell me, what about the sending end power factor and receiving end power factor here? Both are what? 1. But tell me, here what? Sending end power factor is definitely less than what? Receiving end power factor. Why? Okay, before this we have to conclude one more important thing. Chalo, I will discuss this little later. So to get a clarity, tell me, here line act as neither sink nor source for reactive power, because reactive power generation, consumption are same. Transmission line generates the reactive power in the form of what? Because of capacitive nature. And transmission lines consumes the reactive power because of its inductance, series inductance. So finally what I say, reactive power consumption and generation are same. That's why line act as neither sink nor source for reactive power here. Act as neither sink nor source for reactive power. Line act as neither sink nor source for reactive power here. But what about here? Line act as what? Sink or source? Only sink for reactive power. Why? Very simple. Tell me, reactive power consumption is what now? I square XL. Reactive power generation is what? V square by XC. This is what? Q consumption, and this is what? Q generation. Right? Try to understand. Compare it to this case. In this case, we are transferring more power, means more current. More current means consumption is more here. Compare it to this case, here consumption is more. Because compare it to this case we are transferring, loading is more, greater than surge impedance loading, here equal to surge impedance loading. Loading is more here compared to the first case. Second case having more loading. More loading means what? More power you are transferring. More power means what? More current. More current means what? I square XL is very high. I square XL increase. But V square by XC almost same. Okay, slightly, strictly speaking, what happens? V decrease. V decrease means V square XC decrease. So I square XL increase, V square XC decreasing. Here consumption and generation both are same. But here what happened? I square xn is more compared to here. V square by xc is what less. The balance lost. But how it is not? Consumption greater than generation. That's why what happens now? Act as what? Sink. Because reactive power consumption is what now? Greater than generation. So that's why line act as a sink for reactive power. But here reverse. Correct or not? Clear? So here line act as what? Source for reactive power. Line act as source for reactive power. Now tell me, here sending end power factor and receiving end power factor is what? Same. That is what? Unity. But tell me, generally think about here, load or lagging power factor. So receiving end power factor is what now? Lagging. Generally receiving end power factor is what? Lagging. What about the sending end power factor? More lagging or less lagging? More lagging. Why? Why more lagging? Means what? Current lags the voltage by very high value. Why? Because here line is also consuming the reactive power, load also consuming the reactive power. So more reactive power has to come from the source. More reactive power means what? Angle more. Power factor is what? Less. So that's why what I will say under this assumption, practically power factor of the sending end is less than what? Power factor of the receiving end. Here what? Reverse. Power factor of the sending end greater than what? Power factor of the receiving end. Clear? Understand? So that's what you need to understand. Even if receiving end power factor is unity, sending end power factor is what? Less than 1? Lagging. Okay? But here receiving end power factor unity means what? Sending end power factor less than 1. Greater than 1 is not possible. But leading. Instead of lagging, it become what now? Leading. Okay? Clear? Understand? Now tell me. What compensation transmission line require here? Tell me, what compensation transmission line require? Here transmission line require shunt, no compensation required. Why? No reactive power consumption in the line. But here shunt capacitive compensation required. Compensation required. Here shunt inductive compensation required. Why? The line acts as a source. That's why. But before that, tell me, what about the sending end voltage and receiving end voltages are here? I'll write here. What about receiving end voltage and sending end voltage? VR equal to Vs here. Okay. But what about here? Here VR less than Vs, because of more current means more voltage drop. What happens here? VR greater than Vs. This is also called Ferranti effect. Under no load or lightly loaded condition. That means whenever the loading is less than surge impedance loading, na, receiving end voltage become what? More than sending end voltage. This phenomenon is called Ferranti effect. Okay. So yeah, compensation we are talking about already. Now this is what? Ideal loading. Practically not possible. But what about this? Practical loading. This is the practical loading. But what about this case? What is this case? It is what now? Ferranti effect. Ferranti effect. Clear? So these things are very, very important. So with this, we concluded surge impedance loading. So we started with definition. The definition is very simple. You might be studied in BTech what is surge impedance loading. Generally, you study definition, but this much analysis generally you are not done in your BTech level course. But all these things are very, very important. All these things are tested in GATE exam also. Okay. So these points are very important. These conclusions are very, very important. So if you really notice, for every topic I am going to write some conclusions. Those conclusions are very, very, very important. Please be clarity on those conclusions. And even I am not given this conclusion just like that. For every conclusions I given a True, false. For example, let's see here VR and IR are in phase. Why I said VR and IR are in phase? Under surge impedance loading, as per the definition, it's a purely resistive load. Resistive load means what? VR and IR, definitely voltage and currents are what? In phase. Theta are 0, power factor is unity. So everything is what? Just a logic flow. So logically we discuss everything. Let's see under surge impedance loading. Since we are talking about lossless line, these equations long back we derived for lossless line, and from there only what? We proved all these things mathematically. Okay, I'm discussing all the points and I'm giving what now? Mathematical proof. Okay, so please practice them. You should also think like that. Okay, and you have to practice like that. Then only you can remember the subject for what? Long time. Okay, clear? Understand? So that's it. That's about surge impedance loading. We understand now. Now we'll go for the next topic, that is what is the typical value of phase constant beta for lossless line. Okay, this is also very important. Okay, typical value of phase constant beta for lossless line we'll discuss now. If you complete this table, we'll go now. You understand this table, right? Yeah. Now let's see what is the typical value of beta for lossless line. So if inductance and capacitance is given, you can directly take the value, but if it is not given, we have to go with these values. Okay, chalo. What is beta called? First of all, beta is what? Phase constant. Phase constant. Generally, it is expressed in what? Either radian per kilometer or what? Degree per kilometer. Radian per kilometer or what? Degree per kilometer. But what is the formula for beta? We can write omega into root over small l into small c. Otherwise, root over small xl into what? Small bc. Don't forget this. Okay? Clear? Even we can write beta L also. Let me write that. Beta L means what? Omega into what? Capital L into capital C we get. Otherwise, capital XL into what? Capital BC. But careful. This is in what? Degrees. Or what? Radians. Better. Actually, by default, we get it in radians. Or what? Degrees also we can write. Beta L means. Okay. But this is not important for us. What is important is beta. Because beta L is depends on the length of the line. Okay, I can write that separately. Now tell me, what is the inductance of the transmission line? Inductance formula, approximately, what is the inductance? Mu naught by 2 pi, na? Means 2 into 10 power minus 7. 2 pi if you do, 2 into 10 power minus 7 only. Ln of what? GMD by what? GMR. But, what is this? Henry per meter. What about C? 2 pi epsilon naught. Ln of GMD by what? GMR. Farad per meter. Now approximately, actually this GMR and this GMR little difference, because for this GMR radius means we consider R dash, but here radius means just we consider R, to account for flux, internal flux linkage here. But in case of capacitance there is no internal charge, directly we take R here. So that's why exactly GMD by GMR ratio here not same, but approximately same. Since we are doing the approximation, that's why tell me what is L into C product? L into C product will be what? 2 pi get cancelled. We get what? Mu naught epsilon naught. We get mu naught epsilon naught L into C product. Let's substitute that. beta equal to omega into what? Mu naught epsilon naught. Okay, we get it radians per meter. Why? This is by default in what? Meter per meter. That's fine. Okay, clear? Now this is what one thing. But you substitute mu naught and epsilon naught and tell me the value. Omega is what? 2 pi into 50 into root over 4 pi into 10 power minus 7 into 8.854 into 10 power minus 12. Please substitute all these things and tell me what is this, so that we get it in what? By default radians per meter. Now tell me what is this value. If I do these calculations, what I get? Check everybody, you should solve please. 4 5 into 10 power minus 7, yes, into 8.854 into 10 power minus 12, yes, and root over of that into 100 pi. So we get 1.479, 1.0479, 048 approximately, 048 into 10 power minus 6 radians per meter. This is the typical value of beta, but I will write like this, 048, because length of the line is generally given in kilometers. That's why I will write radians per kilometer. Now you can check. You multiply with 180 and divide with pi. Again I am saying, for this number I am multiplying with 180 and divide with pi. If I do that, I will get in degree per kilometers. So that is what? 0.06. Let me write here. 0.06 degree per kilometers. So these are the things we get. Okay, clear? Understand? Any doubts here? That's about typical value of beta for lossless line. Okay, I hope you got the clarity on this. Okay, so we'll solve some problems here. Then we'll go for what is tuned line, and also the power flow equations in terms of ABCD parameters. So these things we have to discuss later. Okay. So let's see this question. Have a look. What is mentioned? A lossless 400 kV transmission line with inductance and capacitance of 4 millihenry and 0.025 microfarads are given. So here the inductance value and capacitance value given. So that's why we need to calculate the surge impedance. Now the line is delivering 500 megawatt power to load at receiving end. That means PL is given. What is PL given? The line delivering power is what now? 500 megawatt. Yes or not? Chalo, fine. First question, what is the ideal power transfer capacity of the line? Ideal power transfer capacity of the line means what? Surge impedance loading. What is the formula? VRL square by what? Z surge. But we need to calculate first of all Zs. Zs equal to root over small l by small c. What is that? 4 into 10 power minus 3 per kilometer. So that's why even here also per kilometer. So we can keep as it is 0.025 micro. Micro means what? 10 power minus 6. If I calculate this, what I get? Check. We get 400 ohms. If you have any doubt, check. Yeah, we get 400 ohms, no doubt. So what is surge impedance loading now? Our ideal power transfer capacity is nothing but surge impedance loading. What is the answer? Such a simple problem is also tested. Okay, careful. 400 square by what? 400 megawatt. Because k square will give you mega. Directly I am writing. So we get 400 megawatt. That's what the surge impedance loading is. And now tell me, what is the second case? Actually, think about here the loading is what now? Load power is 500. Surge impedance loading is 400. Loading is greater than what now? Surge impedance loading. So what happens? VR become less than Vs without compensation. If you not provide any compensation, this is what happens. But what compensation is required? Since line consumes, if PL greater than SIL, na? So line act as a line consumes reactive power. Line consumes reactive power. Reactive power. That is also another reason why VR is less than what? Vs. You can think like that also. So, and to maintain what? To maintain VR equal to Vs, line require what? Capacitive compensation. Capacitive compensation. Otherwise, simply loading is greater than surge impedance loading. That definitely line require capacitive compensation. We already discussed that. Even this kind of question also once given in the GATE exam. Okay, so careful. So that's it. Okay. Now we will discuss what is concept of tuned line and the Ferranti effect. Okay. Now what is called tuned line? Tuned line means what? Definition I will write here first. Tuned power line. So the definition is if sending end voltage numerically equal to receiving end voltage and numerically equal means what? Magnitude. Numerically equal to receiving end voltage and sending end current numerically equal to sending end current also what? Numerically equal to receiving end current, then such a line is called tuned line. Why it is called tuned line, we'll see later, don't worry. But as per the definition of tuned line, Vs equal to VR. Maybe you are thinking that under surge impedance loading also we are getting this, huh? No. Yes, we are getting. But the point is that we don't want for surge impedance loading Vs equal to VR and Is equal to VR. That anyway possible. But for any loading also this is, if this is true now, any loading also if this is true now, then that is called what? Tuned power line. Let's see what is Vs expression. Just recall. VR cos beta L, correct or not? Last class line only. IR Zs sin beta L. What is Is expression? IR cos beta L plus J into VR by Zs sin beta L. Now think about what should be the beta L if you want Vs equal to VR. Beta L must be, beta anyway it's not equal to 0. If beta L 0 means what? Length of the line 0. Cos 0 1, cos 0 1, sin 0 0. That means these terms will gone. Vs equal to VR and Is equal to IR satisfied. Correct or not? For example, think about what I am saying. If beta L 0, what happens? Substitute here, sin beta L 0, sin beta L 0. This term is gone. Cos beta L 1, cos beta L 1. Vs equal to Vr, Is equal to Ir. Acha, beta L0 means what? When beta L0? Think about it. Beta L0 means beta will never be 0. Beta typical value is 0.06. That means length is 0. Beta L0 means what? Length of the line 0. Length of the line 0 means what? This is the point sending end. This is the point only receiving end. What is the need to say Vs equal to Vr and Is equal to Ir? They should be same. If length is 0 means. Correct or not? So that's why this is not a correct thing for us. Chalo. For example, think like this. If beta L equal to what? Pi, 180 degrees. Otherwise 180 degrees. Now tell me, what about Vs minus Vr? Is minus Ir. So Vs magnitude is what? Vr, and Is magnitude is what? Ir. Yes, now it is called what? Tuned line. But tell me, beta L 180 means what should be the length? What should be the length? Beta L 180 means what? What should be the length? Length equal to 180 by what? 0.06 degree per kilometer. So you will get what now? 180 by 6 means what? 300. So 3000 kilometers. That means only for 3000 kilometer length only this is possible. But for any length we want beta L is 180 degrees. The requirement is, what is the requirement? For any given length of the line, for any given practical length and practical loading, we want beta L equal to 180. So that means beta need to be adjusted. But beta should be increased or decreased? Actually beta should be decreased. Why? Because, so length of the line is never be more than 1000 kilometers. Correct or not? For 1000 kilometer length, we want beta equal to what? Beta L equal to 180. Just think about it. Then beta should be what? For example, I have a length of what? 1000 kilometers. Length of the line is originally 1000 kilometers. Beta L I want 180 degrees. Means what should be the beta? 180 by what? 1000. Yes or not? Clear? So what I get now? 0.18 degrees per kilometer. But what is the typical value of beta? We have 0.06 degree per kilometer. But I want 0.06 to 0.18. Means, I'm sorry, beta need to be increased, not decreased. But how to increase the beta? Okay. So what I can say? For achieving tuned line, in practice, what we understand from here, beta L we want any 180 degrees for any practical length. So for achieving tuned line, beta need to be increased. Correct or not? So in practice, what I understand, in practice, beta need to be adjusted to achieve tuned line. In practice, beta need to be adjusted to achieve tuned line. To achieve what? Tuned line. So actually beta need to increase or decrease? Need to be increased, not decreased. Now tell me, what is the formula for beta? Root over small xl into what? Small bc. This is the reactance of one section and this is the susceptance of one section. Either you can increase xl or you can increase what? Bc. But increasing xl is not good. You know why? Line reactance if increases, then stability of the system decreases. So forget about xl. Only option is bc. If you want to increase the bc, already we have a capacitance of the line. bc equal to omega c. Now I need to connect one external capacitor, for example, C external, whose BC is what? BC external. What is this BC external? Omega into C external. If I connect a shunt capacitor. So now overall what is this now? BC dash. That become what? BC plus. Susceptance parallel means you can add it. Susceptance are in parallel means you can add it. BC plus BC external means what? By using shunt capacitive compensation, we can increase the BC. So what I am saying, to achieve tuned line, transmission line require what? Shunt capacitive compensation. That's it. Shunt capacitor compensation. Clear? Understand? So by using shunt capacitor compensation, we can achieve what now? Vs equal to Vr. Okay? Clear? Understand? So that's it. That's about tuned line. And how to achieve the tuned line means by using what? Shunt capacitor compensation. Shunt capacitor compensation. You should be very, very careful. By using shunt capacitor compensation only, we can achieve what now? Tuned line. No other compensation. Definitely we need what? Shunt capacitor compensation for transmission line to achieve what? Tuned line. I hope you understand this. Okay? Clear? Any doubts? Okay? Clear? Now. We'll go to Ferranti effect now. That is our next topic, Ferranti effect. Now what is Ferranti effect and how to reduce the Ferranti effect also we need to see. See, Ferranti effect means under no load and lightly loaded condition, under no load and lightly loaded condition, under no load and lightly loaded condition, the receiving end voltage of transmission line, is greater than sending end voltage. And it is called Ferranti effect. Okay, what is this? Vs is what now? Less than Vr dash. Otherwise, Vr dash greater than what? Vs under no load. Okay, this is what we call Ferranti effect. What is called no Ferranti effect? Vr dash equal to Vs. Sorry, Vr dash equal to Vs. Now that is called what? No Ferranti effect. If Vr dash equal to Vs, then it is called what? No Ferranti effect. Okay, clear? Understand? Now, think about here. So, what is the problem with Ferranti effect? For example, generally around 2 am to 4 am, that means in the early morning, I can say, the load on the transmission line is very less. Under this condition, what happens? Loading may become less than surge impedance loading. Just now we discussed, if the loading less than surge impedance loading, receiving end voltage will increase. That will become greater than sending end voltage. Mathematical proof I will give, but listen, what is the problem with Ferranti effect? So suddenly what? VR become what? Very high when compared to what? Sending end voltage. But at that time, whatever the consumers are connected to the line, they experience with dangerous voltage and consumer equipment insulation will break down. Not only consumer equipment insulation, but also line insulation also going to break down. So that's why Ferranti effect causes what? Breakdown of insulation to equipment. Line equipments, line insulation as well as what? The industrial equipment insulation. Okay, will break down. Okay, so due to Ferranti effect, insulation of equipment, otherwise equipment insulation will break down. Okay, so Ferranti effect causes permanent overvoltage. It's not transient overvoltage. Ferranti effect causes permanent overvoltage. Effect causes permanent overvoltage. Overvoltage, and it results in breakdown of insulation. Breakdown of insulation of electrical equipment. Okay, it results in breakdown of insulation of electrical equipments. Okay, clear? Understand? No. So next important thing is we need to prove mathematical proof for Ferranti effect. Let's see how to prove this. Let's see. Under no load only, if you write under no load, what is for lossless line only we'll see now. Under no load, what is VR dash? Vs by A now. But what about A now? Cos beta L. Correct or not? Clear? Understand? But generally A is what now? Less than 1. Cos of any value except 90 will be what now? Less than 1. Okay? Clear? Cos 0, 1. I'm sorry. Cos 90, 0. Means what? A become 0. Means VR dash become what? Infinity. So what you can understand from here? Beta L 0 means what? VR dash is equal to Vs. But that is impossible. Beta L is increasing. A decreasing. VR dash increasing when compared to what? Vs. Okay. Chalo, A less than 1. What I want to prove is A less than 1. From this, since A less than 1, VR dash greater than what? Vs. Okay. Now, one thing we can write. Beta L increases. What happened? VR dash also what? Increases. This is what I can write now. But what is the formula for beta? Omega into root over L into C. Correct or not? Now tell me the conclusions here. Ferranti effect is because of inductance or capacitance or both are. Both inductance and capacitance. Maybe you are assuming that capacitance only causing Ferranti effect. Okay, fine. But inductance also contributing for Ferranti effect. If I say inductance is anything, Ferranti effect not changing means it's not good. For example, inductance 0, beta 0. For example, inductance 0, beta 0. What is the meaning of beta 0? Cos 0, 1, VR dash equal to Vs. So no Ferranti effect. So that's why technically what I say, both inductance and capacitance are responsible for Ferranti effect. Ferranti effect is due to, is very important. Ferranti effect is due to both inductance and capacitance of transmission line. Both inductance and capacitance. Transmission line. Now tell me. For example, if L0, what happened? Beta 0, A1, VR dash equal to Vs. No Ferranti effect. Correct or not? Otherwise, if C0, think about capacitance 0. Similarly, what? Same thing. No Ferranti effect. Otherwise, if L and C both 0, again no Ferranti effect. Correct or not? Let's say, if L increase, inductance of the line increase, or C increase, or L and C both increasing, Ferranti effect, beta increasing, beta increases means beta L increases, VR dash increases means increase in Ferranti effect. So that's why we say Ferranti effect increases. Ferranti effect increases. Suppose if frequency increases, beta increases, Ferrand effect increases. Length of the line increases, beta will increase, A decrease, Ferrand effect increases. So all these things we can write now. So next one is conclusion number 4. If frequency increases, beta increases, A decreases, Ferrand effect increases. For DC, F0, beta 0, A equal to 1, no Ferrand effect. For DC, there is no Ferrand effect. Careful about this. For DC, there is no Ferrand effect. Is this clear, everybody? Next. If length of the line increases, yes, Ferrand effect also increases. Beta L increases, A decreases. So Ferrand effect increases. Clear? Understand? Next. For short transmission line, no Ferrand effect. Why? A equal to 1. This implies VR dash equal to Vs. So no Ferrand effect. Next. If it is a medium transmission line, you remember? Medium transmission line, A CL is what? Lowest. Then AT equal to A pi. That means parameter A comparison I am writing. And ACS is what? 1. Okay. Capacitance at source and model, A value is 1. So from this what I can write now? For medium transmission line, CL model having highest Ferrand effect. Having highest Ferrand effect. CS model having no Ferrand effect, no Fe. T and pi model having moderate Ferrand effect. Moderate Ferrand effect. Yes or not? Based on A only, we define the Ferrand effect. I hope you got a clarity on this. Okay? Is this clear, everybody? Chalo. Now, the next important thing is how to reduce the Ferrand effect. Very simple. To reduce the Ferrand effect, you can go with what? You can go for what? Reduction in beta. Okay, let me write here. See, we know that beta equal to what? Root over XL into what? BC. So, if XL decreasing means what? How to decrease the line reactance? By using series capacitive compensation. Yes, we can use. If BC decreasing means what? By using shunt inductive compensation. Shunt inductor decrease the BC. So that we can reduce what? Ferrand effect. Okay? Clear? Fe decreases. Ferrand effect decreasing. That means, but which is better? In practice, shunt inductor is better compared to series capacitor because series capacitor having its own disadvantages. So in practice, to reduce the Ferrand effect, we prefer shunt inductive compensation. In practice, to reduce the Fe means Ferrand effect, the shunt inductive compensation is preferred. Compensation is preferred. It's commonly asking question. Shunt inductor main advantage in power system is to reduce the Ferrand effect. Okay, clear? So that's it. That's what the Ferrand effect and its importance is. Okay. So, chalo. So with this we finish the Ferrand effect. I think we have a next analog session, I think. So I'll stop here for the day, and tomorrow lecture we'll see the power flow equations in terms of ABCD parameters. Okay, so that's it for the day.